Yeah. Okay, so in yesterday's lecture, we saw two different methods. The very first was based on expectation, which was kind of deterministic in nature, and it used something known as reduction factor, and that is what we multiplied to our base mortality to get to the forecast of the future mortality. And then we saw another method which was based on extrapolation, and that was called Lee-Carter method. Again, remember, it was not exactly like regression, but it had a structure which is kind of like a regression, but the error terms, especially when we figure out the values of k using ARIMA model, the error terms over there do not really mean what error terms actually mean in terms of a normal regression. So we have to remember the way we can actually, get to estimate the parameters. So you don't have to get into depth of SVD and PCI, I would say, but this is very fascinating. I guess I have give you guys some nice insights into what these powerful techniques can allow us to do. So today we'll be looking back at P-splines that we've already studied about. So this is just a recap of P-splines that they have mentioned here. So yeah, recall from chapter 11 that this is a polynomial of a specified degree defined on a piecewise basis. So each piece is the piece that joins the knots and that we try to create. So always remember, we start off with the knots, but again, you cannot just join them in any manner. There are some continuity conditions that we want to be satisfied. The very first is that the value of the cubic. So when I'm talking about cubic, it means the line that I used to join the two knots, because that is the cubic polynomial that I have used. So again, we use cubic because it gives us the smoothest possible graph. And here we have the value of cubic leading into the knot and leading out of the knot, and that should be equal, right? So we have already seen that it shouldn't be like this and this. So this should be equal, this should be equal. But again, it doesn't matter only if they are equal. The derivative should be, also the same. So the left continuity and right continuity answers should be same, which won't be in this case. So we need something like this. So if this is my one knot, second knot, and third knot. So these are some continuity conditions that we have already seen, and that will make our spline, cubic spline. Basically, it will make it a spline. And if you use a cubic polynomial, then it will be a cubic spline. And if it is linear after the last and before the first knot, then that is known as natural cubic spline. So remember, the function was something like this. So this is alpha 0 plus alpha 1x and the summation of bj phi jx, where phi j is defined in such a manner corresponding to each of these x's being greater than or equal to xj. So remember, what we observe will be x, and xj will be something that we'll be checking on for each of these particular cases. So now let us try to see how we can actually use this. So again, sometimes what you can do is, if you want to construct a model for mortality, right, the very first thing that these guys are doing here is, I think we should look here. So yeah, forget about this. Just look at this thing. We are looking to figure out the log of mortality rate. And we have already seen that we can rewrite our mortality rate in terms of the number of observed deaths and the number of lives exposed to risk in such a manner. So you can rewrite your log of mu x as log of expectation of dx upon exc. And then what you do is, if you just separate the logs, you will get this thing on your left hand side, right? And on the right hand side, you will still have, basically that will be equal to your log of mu x. So now my model previously, in the Lee-Carter model, it was what? It was some constant plus some beta term that was again depending on the age and some k term that was depending on t. So here, instead of having that kind of a restricted model, I'm trying to see if I can maybe somewhat generalize it. So I'm trying to use a Gompertz model. So what I do here is, I rewrite this thing as this alpha plus beta x. So again, just imagine this thing as nothing but, we are saying that my log of mu x is equal to alpha plus beta x. Okay, because log of mu x is equal to log of expectation of dx upon exc. which can be written as log of expectation of Ex minus log of Exc. All right. So I hope this is clear. So you will try to see, but again, you cannot clearly see whether this is Gompertz or not, right? You remember it was something C raised to X. So here they are just trying to show that this is indeed using Gompertz law. So again, remember there is a subtle difference between Gompertz law and Gompertz model. So in this particular case, what I am using is Gompertz model. But again, that relates to Gompertz law. I mean, why is this model called Gompertz model? Because I'm using Gompertz law. So if you have a look at here, this is exactly the same thing that we just saw. You will try to compare it with this particular form of Gompertz law. So now you have mu x being equal to b c raised to x. So what you can do is you can have this thing rewritten as mu x being equal to e raised to alpha plus beta x, which again can be rewritten as e raised to alpha plus, e raised to alpha times e raised to beta x. So if you now try to compare this thing and this particular two expressions, what you get is, so you compare and you will realize that your b is nothing but e raised to alpha and that your c is nothing but e raised to beta. And this is how you see that this is indeed, using Gompertz law. So thus, this actually satisfies. Let me see when clear. All right. So this is what they are trying to do. So here, if we have this sort of a function, we basically are trying to use Gompertz model. But again, this is not actually accurate because most often if you see, we are ignoring the error term that we should ideally have included. So again, here Ex is the random error term with mean 0. And again, there will be some probability distribution that you can assume. Generally, we assume for it to follow normal distribution. And that is why this particular model becomes a stochastic model because you do not know the value of Ex, right? But in Gompertz law, you do know the values of alpha, beta, and everything else. So you can kind of figure out the value, the mortality rate in the Gompertz law. But again, if you're using the model here, this becomes a stochastic model because of the very nature of the error term that we have here. All right, and now what they're doing is, so this alpha plus beta x is just a linear function, right? So previously we did make an assumption that my mortality is, I did not start the recording. No, I have. Okay. I don't know what happened. Okay, yeah. So what I was saying was that for now, what we assumed was that we have alpha plus beta x, right? Which is sort of a linear function. And why? Because we sensed that normally, at least in the middle and older ages, my mortality I see follows exponential distribution. It has an exponential curve, not exactly exponential distribution. So sorry, I'm correcting myself. It has an exponential curve. So I sense that if I put logarithm on my mortality rates and my actual mortality rates, then I will get something which is a linear function. And that is why the very first thing that we tried was alpha plus beta x, which is a linear function in age. But again, this might be very helpful in some cases, but need not be helpful in all the cases. So sometimes you would need some function which is much more flexible. So what you do is you use spline, and this is where your splines come into picture. So this is the function that we know changes, right? From one knot to another knot and to another knot. So in every particular piece, you will have different functions depending on the kind of fruits that you observe over there. So here, instead of just having this particular function, we take this P-spline here. So again, these are the set of splines that you use, and theta j are the parameters. So when we studied splines previously, we used something else. So yeah, beta j, and we use this as a function. So here bj corresponds to this function and theta j corresponds to this parameters that we denoted as beta when we studied this particular topic in chapter 11. So just remember that difference. It doesn't, I mean, it's just the notation that is different. The functions will still remain the same. So now you have a much more flexible model again for the log of mortality rate. So here again, if you do the same thing, that is what they have just proven that, yeah, this is indeed basically the same thing. So nothing much new over there as well. Okay. So now here, I guess they are just talking about how this particular method is helpful and how this might sometimes lead to problems. So now whenever we're talking about p-splines, well, we know that we are making various changes in the, I mean, we can make various changes in the number of knots that we put, right? So if we see that in the younger generations, especially during the infant, let's say, or teenage, or let's say childhood, we see some sort of a pattern. We see that there is, I mean, the data is not actually smooth, and that is the characteristic of the data. It is not that it is, basically not smooth because we couldn't find a smoother function, but it is not smooth because that is how it behaves in actual. So then you can actually use knots, and you can put more knots in the younger ages, so that you get piece by piece, little approximation, which will be good fit to the actual mortality rate that you might expect around those particular ages. But again, sometimes, so it's very difficult for us to know if we do not have any prior expectations. So let us say in males, it is generally seen that around in the 20s, there is an accident hump. So now we know that information, right? So if we see some particular function jumping around those numbers, then we would know that this is not something which is only happening. I mean, this is something which is only going to happen in these ages, right? It's not going to happen later. So then you will have to kind of not take those into consideration if you're using today's age to figure out something about tomorrow's age. But again, if you're using today's time to figure out something for the next time, for the same age group, then you can clearly say that, yeah, we will still expect the harm. So sometimes there are these short-term variations that you might expect to continue, that you might not expect to continue, depending on what your purpose is. And that is where this spline could actually be helpful. But there is some disadvantages as well, because then if you always try to use more number of knots, then you will see that the fit is always better. So anyone will just try to put as many number of knots as they will want to, right? But then what will happen is the graph that you will get will be not smooth. It will be rough. It will be like point to point. So the very purpose we're using p-splines is to not have a rough graph, which we would get if we just join the crude rates, right? So this kind of negates the whole purpose of doing this exercise. So what you do is you try to add a particular penalty term, which will basically compromise, which will try to reduce the likelihood in case you try to put in more and more number of knots. So now if you see here, what they're doing is, so they have just showed us the whole method of how do we go about, figuring out the likelihood function to then, which will basically help us to then figure out the parameters and so on. So here, the very first thing that we do is we specify the knot spacing and the degree of polynomials. So generally we use cubic and generally the knot spacing. So again, knot spacing need not be equally spaced always. It can be in any manner you want. And then you define a roughness penalty here. So here they're talking about this roughness penalty, which they denote it as p theta. And this is not working. Give me a minute. Yeah, so basically you define a roughness penalty p theta and you assume basically, so again, this is a penalty, right? For what? For when your graph is much more rough than what you need. So this will increase if you increase the number of knots that you have. So more than what is required. So if you look at this again here, these are the parameters, theta 1 hat, theta 2 hat till theta s hat, because we are taking this thing to go till S. Yeah, so J goes from 1 to S, and that is why you have S number of parameters apart from the ones that you have already in the starting. So here, then you define a smoothing parameter lambda. So such that when you put lambda equals to 0, you know that there is no penalty for the increased roughness. But as your lambda will increase, your roughness will be penalized more and more. So this is much more clear if you look at this particular formula. This is the actual likelihood that you get And this is the likelihood that you will have without including any penalty term. And then you include this particular penalty term. So what you're doing is this is minus a half just for some correction, and you have this lambda here. So that if you just want this penalty term to not affect this particular thing, then you will put lambda equals to 0. So you have much more control over what will affect your likelihood and in what manner if you include a penalty term. So again, your penalty term is a function that you can define in any manner you find suitable. So we will see an example that they have given here, which will actually show us how to draw a penalty graph. So again, yeah, the penalized log likelihood is basically effectively trying to balance smoothness and adherence to the data. So we know that we will choose the values of the parameters that will maximize this LP theta, right? So again, the value of this particular thing increases if you have a smoother function. And again, if you have a rougher function, then this particular value will be decreasing in nature. So in a way, this kind of balances if you have a penalty term here. So that is what they're trying to say over there. And now here they have showed us a penalty function. But even before we do that, let us have a look at this particular thing. So this is how they have defined a penalty function. So my f of a comma b comma c is equal to c minus b minus a. And why? Let me just show you guys. So let us say this is my a, this is my b, and this is my c. So yeah, now these are the things, and I want this particular graph to be smooth, right? I do not want it to be very rough. So what I would expect is that the difference between the differences is kind of small, right? And that is what we look for. So what you do is you look at the difference between B and A, and you look at the difference between B and C, and then you subtract those two. So what you're doing here is C minus B, then B minus A, and then you subtract both of these from each other. So this is like taking the second difference. You take the first difference, and then you again take the difference of the differences. So this is like taking a second difference. And just to give you an example, we can now just say that, 457 is much smoother than 475. This is evident to this is clear, right? So if we try to substitute these values in this particular function, what you get for the first case in the penalty term is 1. And for this particular case, you get minus 5. So now you know that, you would have expected a higher number for this particular, right? It is 4, 7, and then 5. So this is not as smooth as this particular guy. So now you want to take this. So now basically what you will try to do is you just square this. And that is the same thing that they're doing here. So what they're doing here is the penalty term. They've defined it as something like this. And now they're trying to show that this is nothing but the second difference squared. So square of the second differences. So I guess we have already discussed in the previous lecture. And for those who haven't studied time series, I would just say that whenever I'm writing, let's say, RT minus 1, this is something that I denote as delta R. So this I call as del R. And RT minus 1. And this I denote as basically del R. So I'm looking at the very first difference of this particular guy here. So again, I think okay. So sometimes you write it like that. So here again, they are just using this particular difference to rewrite these things. So this function that you have, minus 2 theta 2, they have just expanded it as minus theta 2 and minus theta 2 to give you the first difference, second difference, and the differences similarly. So I'm just going to follow this particular one term here, and you can do the similar thing for all the rest of the terms. So here I have theta 1 minus 2 theta 2 plus theta 3. I can rewrite this thing as theta 3 minus theta 2 minus theta 2 minus theta 1. Why? Because this minus and this minus will make it a plus, which is exactly what you observe there. So now this is like C minus B, and then this is like B minus A. And now what you do is this is nothing but delta del theta 2 minus del theta 1, and you are basically trying to square it here. And then if you look at this particular thing, this is equivalent to the del of del theta 1. So you can rewrite this thing as del square theta 1 and the whole thing squared again. So here they are just saying that del raised to r indicates the value of the rth order difference. So here this is the second order difference of theta 1. And again, now what you will want to do is you want to take theta values such that your penalty is as minimum as possible. And this is just in the example that they have given to corroborate that. Yeah. So again, here when we square the function, it ensures that we have the values getting penalized much more wherein there is roughness, because we saw, right, 457 got the penalty as 1 and 475 got the penalty as -5, and we would have expected the opposite. So you take the absolute and you square it, and that will allow you to have a proportionally greater penalty for the larger absolute differences. And that is what we think will ultimately result in a smoother final outcome. So once we have estimated the parameters by, let's say, maximizing the actual likelihood, which also includes the penalty term, then you will try to forecast, right? So once you know all the values of these thetas, you can figure out the values of beta j's, and this you will know, so you can figure out the number of deaths and all. And essentially what you are trying to do is figuring out the value of mortality using this particular thing here. So again, here they are just explaining that if x is an integer and we are ignoring and we are grouping the data by age nearest birthday, then mu and m are essentially the same, because x minus a half and x plus a half. The central rate of mortality will be just mu x, right? And m is also the central rate of mortality. So they will be basically the same. So mu x is indeed equal to mx. Otherwise, sometimes you will have mu x plus half or sometimes mu x minus half. Then that will be equal to mx. So the age will differ. So only in the age nearest case, you have age as the same. Okay. So now again here, what happens is they're just saying that you use the past data and then you will try to fit it and try to forecast using the p-splines. But again, there is something else that happens. So once we decide how much forward in time we want to forecast, then you will try to add some dummy variables. So again, what you do is basically you have the whole data set, right? You have observed how many number of deaths deaths in the data set that you will use as your historical data. And then you will estimate some sort of dates, some sort of number of deaths that you expect to happen in the times when you try to forecast for the mortality. So while estimating the parameters, you want to make sure that you only take the historical data into account. So whatever it is that does not qualify as your historical data, you will just give them a weight of 0. And whatever is in the history, you will give them a weight of 1. So that is what they're talking about when they say that, we add to the data set dummy deaths and exposures for each year in the forecast period. So whenever we are, let's say if you're trying to forecast after X, then from X to X plus T, you will put a weight of 0 only when estimating the model, right? So you have to remember that they're only given a weight of 0 when estimating the model. But when you try to forecast, we'll try to use that number as well to figure out our actual, at least the expected mortality in future. So I guess that's it about p-splines. And again, there is a package which they mention here is something like mortality smooth. So you can use that. So I think these packages make life much easier. So again, coming to the advantages and disadvantages, this is again not a foolproof method. And the very first advantage is that it is very, very straightforward to implement in R. So that is something that we always look for. But again, disadvantages. So the graph that you will get can be rough. But again, we have seen a way to overcome this particular thing by adding some penalty factor. But again, you're still not guaranteed. So what they try to suggest is that you not only use functions that depend on age, but also add some time dimension, also add some index, which will allow the time trained to take effect in the calculation of the forecast mortality. And the second is that there is no explanatory element to the projection. Because see, here there is no natural interpretation that we have to compare two different kinds of functions, because splines differ within themselves. So there is no natural interpretation as we saw in the case of Lee-Carter model. And here they're saying again, this tends to be over responsive to an extra year of data. We saw something similar happening with the Lee Carter as well. So we should always be careful when we are looking at the edges of the data, because normally on the edges, it doesn't quite fit that well. I mean, that is what they say by experience. So if you're trying to predict what's going to happen in N+1, then that might be much of what you would expect it to be like. Okay, so now when they say that you should take these age and time into consideration, they've tried to combine Lee Carter model and the p-spline approach here. So this is something that you will get here. And again, I think this is very best explained with the next example that they have given. So because we've already seen, right, in the very first example that we saw in the reduction factor, we saw that a table has rows and columns. So in column, we know that it differs across the time as well. And in rows, we know that mortality differs across the ages as well. So that is why here, if you see, again, they have kind of interchanged this thing here. Previously, we had KT and then BX. So remember this term here has replaced this BX KT that we had in this particular model. So here, these are the basis functions and these are the time series coefficients. So again, the way you would use the ARIMA models to figure out this value of K, you can do the same thing here as well. So you can try to see if there is a trend or something. And yes, we have included an error term here as well. So forget this. I think this particular example summarizes, and if you're still confused about what's happening here, I think this example will clarify it. So here what we see is, basically I'm just trying to explain the second term, which is the multiplication of these two, but we can have a look at this particular chart and see. So whenever I'm talking about summing up these terms for J number of times, capital J number of times, it means that I'm categorizing my data into those many categories. So let us say if I only have two categories, one smoker and two non-smoker, then I will have addition of KTJ times BJX 2 times, right? One and second for a smoker and then for a non-smoker. So now if you see, again, these are assumed. This you will plot the K and you will try to estimate these functions using ARIMA. And once you estimate the parameters, let's say you get this particular functions for non-smoker and smoker. So if you see here, for the non-smoker case, we have this thing as 0.08. And for the smoker case, we have this thing as 0.04. So what do you guys think you can conclude from seeing the slope of the time trend here? So what do you guys think? Which one is steeper in your case? So again, if you kind of forget about this minus sign that you have, we know that if at all I'm trying to plot a function, this is flatter and this is a steeper graph, right? So wherever I get a much more angle, that is a steeper curve. So here, if you see, it creates a lot more difference. So this guy is way steeper than this particular guy. I mean, double the angle, right? So again, what you can conclude is that for non-smokers, the time trend has a greater effect, because for 1 unit of change in time, here you will see a decrease of 0.08. But here you will see a decrease of 0.04 only in the number. So you forget about these constants because these will remain the same. I'm trying to compare my KT-NS today with KT plus 1 NS. So this 1.6 and this 0.8 will cancel. I think maybe I should write it here. So if I'm doing something like this, NS minus KT comma NS. So what do I get here? Here I will have 1.6 minus 0.008 T plus 1 minus 1.6 plus 0.008 T, right? And what is my answer? 0.008, I guess minus, right? So there is a higher effect in non-smokers compared to the smokers guy. So for smokers, you will have 0.04. Oh yeah, this is 0.8. Yeah, I guess you guys get the idea behind this particular thing. So the slope of this particular K will dictate which one of these categories will have a greater time trend effect. And that is nothing but just shown to us by the very coefficient that we have in our formula for K. Okay, so now if you see the next thing that we have here is BJX, and now this varies across ages. So 40 and 60. These are two different kind of ages that we're looking at. So now if you try to compare this B for a person who is non-smoker and age at 40 and a person who is non-smoker and age at 60, you see that this is greater for the younger person. And again, here this is greater than the younger person. So if you see for younger ages, the time trend has a greater effect, right? So I would say, so when I'm saying time trend has a greater effect, why? Because once I fix my age, then what is changing? Then only I'm allowing my time to vary, right? So, and these two get multiplied to each other. So even if I have this particular thing as same, this is going to tell me the difference between non-smoker and smoker. And this will allow me to tell the difference between the two particular age groups that I might look at. So here in the next thing, what they're saying is that the time trend has a greater effect for younger ages than older ages, right? Because in all cases, B40 is greater than B60. So it's same for non-smoker as well as the smoker guy. But again, now you can have a look at how much of a difference do you observe. So there is more of a difference in the smokers, right? So again, it is bigger for smokers than for non-smokers. So this might be, we are only looking at two categories and we are only looking at one particular comparison, but this is normally how you will compare it across if you have multiple ages and multiple time periods to look at. So this is exactly how you will use the P-splines to have some flexible graph and then try to project and forecast your mortality rates. So this was about the explanatory method. Any doubts, anyone with this? Anyone? Was I too fast? Can you guys hear me? Hello?
Yes.
Oh, okay. Thank you very much. All right. So now we'll move on to the next method that we have. This is actually one of the easiest method, which is method based on explanation. So here they have, let's take the example that they have given us. So they're assuming that there is some cancer research study that has been taken place this year, which has led to some big revolutions in the way people used to tackle cancer. So now they are not at the same risk at which they were in the previous year. The risk has decreased and there is something that they can do. There is some new technology and new operation that you can do, let's say, on the people to tackle cancer. And yeah, this is something that, let us say, what we have observed. So here I would like, let me just do it. So suppose the current mortality rate is 0.01 per annum for people aged 70 and people include only males. So analysis reveals that the cause of mortality at this particular age is 35% due to heart disease, 40% due to cancer, and 25% due to all the other causes. So now there is an introduction of a revolutionary new treatment, and they predict that the next year, mortality rate of males aged 70 due to cancer will be 90% of the current rate. So of people struggling with cancer, the mortality rate will be 90% of the current rate. So it has reduced by 10%. And now at the same time, they're predicting that the mortality rate due to heart disease will increase by 2%. So these we expect to increase by 2%. And again, with the other causes, they're talking about an increase by 1% of their current rates. So again, these are the three things that we are observing. So the very first question is to give a possible reason why the deaths from causes other than cancer might have increased. So there is only one revolutionary new treatment in the case of cancer. So why is it the case that other kind of mortality rates might have increased? So the reason that they argue for here is that even though the number of people now dying due to cancer is decreased, those people are still suffering from cancer, right? So they are more likely to die from other diseases as well. Let's say, the heart attacks are common. So you might see someone being treated, but again, still be failing to a heart disease. So that is what they argue, and that is how they assume that these particular rates, other kind of rates, will go up. And now the next thing that they're asking us to do is calculate the expected population mortality rate for male lives aged 70 in 1 year's time. So this is something which is very interesting. So now we know that the mortality rate for males is 0.01 per annum. So the very first thing that you will do is you will try to categorize these numbers as using 35% for heart, 40% for cancer, and 25% from the other causes. So now if you look at the current rate of mortality in proportion, this is what you have, and in total it adds up to 0.01. So this is somewhere, this can be said, the proportion of people who die due to heart disease, proportion of people who will die of cancer, proportion of people who will die of other diseases out of all the people who actually die. So then there have been some changes that we expect. So in heart diseases, we expect the number to increase by 2%, which is why you have this thing getting multiplied by 1.02, with cancer 0.9, and with others 1.01. And this is what you have. So you add them up together, and this will be your predicted mortality rate for the next year. And that is it. That is all you have to do. So now generally, again, this is not as easy. We have data on the number of lives that are alive. We have data about the number of deaths that we have observed for some particular ages, and we have the respective mortality as well. So here LX, expected number of people surviving to the exact age X. So this is nothing but our exposed to lives column. This is the number of deaths column, and this is the mortality column. So here they're asking us to write down a formula for QX in terms of LX, DX, or both. And this is not new. We've already seen this before. So let us try to do this particular thing here. So now there's another scenario that they're giving to us. So they're saying that there is a 10%. So they're saying that 10% of the deaths at each of the ages shown in this extract are caused by a particular type of cancer. So out of all the deaths at the ages that they have discussed, which was 65, 66, and 67, they're saying that the number of deaths that we have, out of these, 10% are observed due to cancer. So here 194 deaths, and here 209.7 deaths. Or weird that might sound. All right. So then they are saying that a new cure for this illness has been introduced that is expected to halve the deaths from this cause in the coming year. So the number of deaths that we see will become 50% of what we observed in the previous year in the coming year. And then it eliminates them completely in the years after 1 year. So that is the environment that we are currently in. And now they're asking us to consider a cohort of people currently aged exactly 65, who in the absence of the new cure were originally expected to follow the mortality of ELT 15 tables over their next 2 years of age. But again, we know that there have been a revolutionary treatment and there was some cure discovered, blah, blah, blah. And that is why these mortality tables rates are no longer the true ones. So you want to re-estimate those, you want to recalculate those, and how will you do that? So in the very first year, we will try to first figure out how many number of deaths were observed due to cancer. And then it was said to us that the expected number of deaths due to cancer will halve in the upcoming year. So you subtract 0.5 times 194. Oops. So what we will do is we will subtract 0.5 times 194 from the total observed deaths, because these many less number of deaths we are going to observe now. So this will be your new rate of new number of deaths that you will have observed at the age of 65 after 1 year. right? So in the very first year, you still observe 1940. And then in the second year, instead of observing 2097, here, instead of observing 2097, what you will observe is something like this, 1843. Oh, wait. No. Give me a minute, I guess. Yeah, sorry. So this is still D65, right? So here what we are trying to do is, we are trying to say, we're still talking about the people aged 65. We haven't gone to the people aged 66. So we still have to look at the very first line itself. And we are talking about changes in the years, not in the ages. So let me go back to what caused me the confusion. Should always be aware of such kind of things. So here, this is for people aged 65 and this is for people aged 66. And we are only looking for people aged 65. So this is what we're trying to compare against. So this will be your DX for a particular year. And then in the next year, you would expect it to become 1843. Okay. And then what we see. So because now the number of deaths have been changed, your mortality rate will also change. So this lives, the number of lives that were alive will still remain the same, right? Because even though the number of deaths have changed, number of lives exposed to that particular risk is not going to change. So you calculate the new rate of mortality, which is something like this. And now once you have this particular rate of mortality, you know that if you are looking for something in the next year, which is again, if you are trying to figure out the revised number of expected survivors at age 66, if the number of deaths have changed, then the people who are alive at the age of 66 will also change, right? So what you do is you have this, your EX from the, so this is what, this is LX 79293 from the table itself, but the new number of deaths that you expect to happen over that particular age. And that will give you your new exposed to risk. So this is how many, this is the number of people that you will expect to be alive and exposed to the risk of being dead when they're aged 66. And once we have this, we know that the people who die due to cancer are eliminated completely. So that you will use to figure out the new rate of mortality. And again here, you can just basically the mortality rate at age 69, 66 will now be reduced to 90% of its original value, as it has already been discussed here, I guess. Yeah, I think we have discussed this in previous. So here, if we are saying that the 10% of deaths at each age is shown in the extract are caused by the particular type of cancer. So we see that these many number of deaths were caused by the cancer, which is what, 194. So now what you have to do is, you have revised the LX for 65, which is nothing but the same. You have revised your DX for the age 65, and you have revised your LX for the age of 66. So the next thing that we want to do is, you want to see how many, what is the rate of mortality for the case of people aged 66. And for that particular case, we are saying that it just reduces to 90% of its original value, because all the 10% deaths that used to happen due to cancer are now eliminated. I guess it was said somewhere here, right? Yeah. So here they say that, right? It eliminates them altogether in all years thereafter. So that is why you will expect no deaths due to cancer at least. So these mortality rates, so again, why do we multiply mortality rate with 10%? Because 10% of the deaths out of the total deaths were observed due to cancer. And now these are no longer observed. So all you are left with is the 90% of the original value. And that is why whatever mortality rate you had previously, you just multiply it with 0.9. So this is the answer that you will have for this particular case. And then again, once you have this particular mortality rate, you can use that to figure out your DX, which is nothing but 1890. And then you can subtract that from the exposed to risk lives, and you will get this particular number, which will denote the exposed to risk for age 67. And that is how you will try to change the type, change basically the calculated values and recalculate it using the new information that has been added. And again, you can do this for multiple state modeling as well, where you can have these people moving from healthy to some disease and then dead, or healthy to some another disease and then dead. So healthy, sick, dead, blah, blah, blah. They're just trying to explain that over there. And at the end here, this is very important. So here they are saying that it might seem surprising that progress in using explanatory approach has been limited. So the very last thing that we studied, it's a bit limited because again, you require specific data, right? You would never know that 10% of the deaths, I mean, you would know that 10% of the deaths are due to cancer, but again, you would not know how much of an effect this new treatment has. So there should be some sort of specific data that you have. And again, here you would require longer lags, because once we have a new invention, to even check how much it affects, to even check how much of a rate of these disease, of people dying due to this disease is decreased due to this particular invention, you need a whole lot of historical data just on the basis of that. And throughout that time period, the mortality keeps changing. And again, what these people do is they set up committees, they will calculate the mortality rates. So let's say they started at 2000 in the year 2001, and they revised the estimates by the end of 2002. And what you will see is there was some new invention developed right in the middle of 2001. They won't be able to take that into consideration. And by the time they will take that, there will be something else that is happening. So again, these errors are not really that you can, hedge against, but yeah. So again, here they are just trying to see some disadvantages. So yeah, causes of death often act synergistically. This is very important because most often a person might be, canceric and might die due to a heart disease. So you never know what exactly caused the death. Was it cancer? Was it the heart failure or whatever else? So most often people do not even report the cause of death. And sometimes you might not know that. It could be just because the person was old or something else. So again, there is this sort of issues. The time series of data is often rather short because the kind of data that we will have is of the people dying due to a particular cause. So first of all, people dying itself is a very, the kind of data that we have for people dying is limited. And then you're again limiting it to the specific causes of people dying. So that will again shorten the span of the data that you have. And that might create some problem because you at least expect there to be some big amount of data to say that whatever study you're doing is substantial enough and holds enough evidence. All right. Oops. Sorry. So yeah, so here they're just trying to, so now that we have already seen what are methods we can use to forecast our mortality rate, we just have to remind ourselves again of the kind of errors that we can see in our forecasts. So here model misspecification, the formula of R is wrong. The P-spline that you use, it shouldn't be cubic or something else. Then there is uncertainty in parameter estimates. This is clear and incorrect judgment or prior knowledge. So again, the data set that we use might not accurately reflect the mortality we wish to model. So let us say you're modeling for non-smokers only, and the data that you're basing this on has smokers as well as non-smokers. So that might create an issue, right? So incorrect judgment. And if you, let's say, don't know about these particular peculiarities, then you might not take them into consideration, which might lead to an underestimate or overestimation of the mortality rates. If at all there is some pattern between what you ignore. So the fourth thing that they're talking about is random variability. Yeah, I mean, this is expected, and errors in the data. So yeah, these are again another kind of errors that you can see. But again, so here what they talk about is that what you can do is you can actually use a method known as bootstrapping to see how much of the parameter uncertainty that you have. So when I'm talking about bootstrapping, what it does is, so see again, what we do to estimate a parameter is, we know we have a population which we can never observe. So we create a sample which accurately reflects the characteristics of the population that we want to model. And we use the MLE or whatever methods we want to use to figure out the parameters from the sample that we have observed, right? So when I'm talking about bootstrapping, what it means is that you're trying to sample again and again. So instead of assuming population is something that you cannot observe, assume whatever sample you have is your population. And then what you do is you do not use all of your sample at once. You use sets of samples. You create sets of samples, and that might be overlapping. It doesn't matter. You randomly pick samples, and you can define a number of, you can define a number that you want to take 40, you want to take 50 numbers, and blah, blah, blah. If you have, let's say, a total of 100 numbers, then you will not use all of those numbers at once. You will try to estimate the parameters using, let's say, 90 numbers every time. And those 90 numbers you pick randomly. And you will get different estimates for the parameter. And then you can actually see how much of a variability you will expect from the parameter uncertainty itself. And that is something that can be used to analyze how much uncertain you are in terms of the parameters that you have estimated, so that you can be careful about the decisions that you make. So whenever you will, let's say if you're working in a company or something, you try to present a report, you will not only project to them the numbers, you will also put caveats. I mean, you'll have to write the caveats, right? Oftentimes it's more helpful if we can put a confidence interval, because that will allow you at least a guarantee, because a point estimate could be like 100% right or 100% wrong. So sometimes there is a tendency for some numbers to be more high, for some numbers to be lower. So it's better if you can do some sort of error hedging. And again, this is just something that you can make them aware of. And it's up to them for them to follow, not how much of a risk appetite that they have. It will depend on that. And again, here, the next thing that they talk about is forecast errors. So here they're talking about the errors being correlated either across age or time. So again, we have seen that if there is, let's say, some error in the tables that we are using as historical data to forecast the next set of mortality rates, then the errors are going to carry forward. But the kind of error that they are talking about here is the one that you see across ages or across the time. So once, if these errors are positively correlated, then the prediction interval will widen. And that is what basically we will believe the future mortality to lie in, but it will not be the case. And if it is negatively correlated, then we expect them to cancel out. So one will be positive, one will be negative, and same numbers, they might cancel out. So, but normally whenever we do these kind of analysis in actual applications, we observe positive correlation, which might really, solve a problem. So they have given an example here. If a large reduction in the mortality rate at age 70 occurs as a result of a new medical treatment, this is likely to affect the mortality rates at neighboring ages as well. So now what does this mean is that basically always we are trying to look at a particular age group, right? So they're just trying to say that this particular new treatment that has been enforced now will not only affect for some people in exactly at the 70 years of age, but also for some people who are 71, 72, for some people who are 69, 68. So we expect the errors to be positively correlated, because if the mortality rate for 70 is reducing, then there is a good chance that the mortality rate for 71, 72, 69 is also reducing because of the same medical treatment. So the kind of error that will be created in the mortality forecast of this 70-year-old guy is the same kind of error. We can expect the same kind of error with the same number, maybe not the same number, but maybe the same sign for the neighboring ages as well. So you see, these errors will be not independent, and they will indeed be basically positively correlated to each other. So that might create some problem, because errors should never be correlated. And if you see some pattern in the error, then of course there is some sort of variation created by some variable that you might have ignored. So you should try to look out for those variables and try to take those into consideration. And that is the end of this particular chapter, guys. Any questions with what we have discussed up until now? Anyone? So I guess that is it from my side for today. The questions at the end of the chapter are again very theoretical, so I would just encourage you all to go through them once, and yeah, do let me know if you have any doubts or is there anything that I can help you guys with.